Well, today the topic of our discussion is White Dwarf. Now, before I talk about the White Dwarf, let me first talk about the ultimate fate of a star. Well, you see, the ultimate fate of a star, what does it depend on? Basically, it crucially depends on the mass that remains in the central core, that is mass in core of star. When fusion can no longer maintain the pressure, so basically ultimate fate of a star depends on mass in the core of the star. When fusion can no longer maintain the pressure needed to prevent the gravitational collapse, gravitational contraction or collapse. Now, what happens is that at this stage, the star must rely on a non-thermal source of pressure for support. And what is that? It is basically a gas of degenerate electrons. However, we do know that hydrostatic equilibrium becomes precarious if gravity is opposed by the pressure generated by ultra-relativistic particles. Now, this general principle imposes an upper limit on the mass that can be supported by the degenerate electrons. Okay. Now, if in fact I have shown you in the stellar structure class, there I have shown you that if the mass of a stellar core exceeds a critical value, the degenerate electrons become sufficiently relativistic to render hydrostatic equilibrium impossible. And then that particular critical mass where this happens, this is around 1.4 solar masses and is known as your Chandrasekhar Mass. So, well, of course, we will be coming to this and we will show you these things. So, basically, the fate of an evolved star depends crucially on whether the mass in its center core, so basically this mass, whether this is less than or greater than your Chandrasekhar mass limit, which is around 1.4 or 44 solar masses. Now, you see, what about our sun? So, our sun basically will develop a stellar core with mass, of course, less than 1.4 solar masses, and which can be supported by the pressure of the degenerate electrons. Now, after it loses its outer tenuous layers, it forms a white dwarf. And this is the topic of today, which is basically a compact object with radius of around 10 to the power 7 meter and the density of 10 to the power, so radius of around 10 to the power 7 meter and density of around 10 to the power 9 kg per meter cube. And this slowly cools without appreciable contraction. Why? Because its mechanical support is due to a pressure which is insensitive to temperature. Remember the equation of state of degenerate electrons? You will not find any temperature over there. So, it is independent of temperature. Now, what happens to even heavier masses? Well, more massive stars, basically, they develop onion-like structure with a central core of iron. So these ones here. So onion structure. Of course, this structure is over here as well. We will show these types of possible white dwarfs. Onion structure with iron in the core, central core. Okay. Now the mass of this inner core basically grows as silicon burning deposits more iron, and eventually the core will collapse catastrophically when its mass exceeds the Chandrasekhar level over here. Now we will talk about these details in another class, but today let us concentrate on white dwarfs. So basically what have I told you? What I have told you is that a white dwarf is basically a degenerate dwarf star. Basically is a remnant of the core and composed mostly of degenerate electrons. Okay. So the next question is, what's the simplest type of white dwarf? So white dwarf, degenerate dwarf, core remnant, and it is mostly made up of degenerate electrons. It doesn't mean that ions will not be there, atoms will not be there, but the pressure due to the degenerate electrons will be much more. I will show it to you. Now, what is the simplest example? Simplest white dwarf. The simplest white dwarf is basically results from the collapse of a star of very low mass. How much? Say, collapse of a star, say mass much less than 0.05 solar masses. And what happens is that here no helium burning is there. And so what will happen is that as a result, since no helium burning occurs, look at the mass, it is very low, so the central temperature is not very high, so no helium burning, and as a result the core is entirely made up of helium. And so this simplest white dwarf is known as helium white dwarf. You must remember. So the simplest possible white dwarf. Okay. Now to look into the physics of the white dwarf, let us talk about the equation of state. Now I have already discussed a lot about the very basic ideas of equation of state for a degenerate matter, particularly electrons. Okay, non-relativistic case, ultra-relativistic case. Okay, but of course for t is equal to 0 case. Yeah, I have also somewhat discussed the finite temperature cases, but now what I am going to do is that I am going to use those results that we have discussed previously. Now you will see that when I write the equation of state, sometimes I am writing in terms of k in r rho to the power 5 by 3. Now here what I am going to do is I am not going to write that constant k of the equation of state. Instead I am going to write the full form. So let us start with the equation of state for non-relativistic case. So non-relativistic degenerate electrons, and you know what does the equation of state looks like. Let me write it down. So the pressure due to electrons is basically, I am writing down the full form, 3 by pi to the power 2 by 3 h square divided by 20. This is mass of electron, mass of proton to the power 5 by 3, and here z by a whole to the power 5 by 3, and the familiar density dependence of rho to the power 5 by 3. So as I was saying is that the most important feature is the absence of temperature. In this equation of state. Okay. Now, let us get some familiar values. So, for a typical white dwarf, let me write the density. So, here we can have, say, example. So, for a typical white dwarf, of course, we can have densities of the order of 10 to the power 6 gram per centimeter cube, and temperature is of the order of 10 to the power 7 Kelvin. Okay, now you see white dwarfs are generally composed of material that are processed by nuclear reactions into helium, carbon and oxygen. Okay, so mostly helium, carbon and oxygen. As a result, let us just assume that Z by A, okay, is approximately equal to 0.5. So if we plug in these values over here, then you can check that we get the value of electron pressure of the order of 3 into 10 to the power 22 dyne per centimeter square. Fine. Now you must be thinking, sir, this is okay, this is good, fine. So, but what about the nuclei? Of course, nuclei are also there in the white dwarf. Now, you see, as opposed to the electrons, the nuclei at such densities are still completely elastic. So, nuclei are still classical at these densities. Okay, and the thermal pressure due to the nuclei, let us calculate, and let us now consider the simple helium white dwarf case. So, the thermal pressure for them, P thermal, assuming helium composition, so we can write rho by 4 mass of proton into kBt, and if you work out the details, you will see that this pressure of ions or atoms, ions, right, nuclei, thermal pressure, it comes out to be 2 into 10 to the power 20 dyne per centimeter square. So, who is the one dominating? Of course, this PE is much greater than your P thermal, right? So, we just have seen that indeed at such densities, the degenerate electron pressure completely dominates the pressure in the star. Fine. Now, let us talk about some of the physical properties of white dwarf. So, physical properties. The first physical property that we are going to discuss is the mass-radius relationship. Fine. Now, what I am going to do is I am going to do a sort of scaling type approximation. We have used the scaling laws. So, let's start with the equations of mass continuity and hydrostatic equation. So, from equation of mass continuity, we get rho of the order of m by r cube. Equation of hydrostatic equilibrium, we get continuity equation. Hydrostatic equilibrium equation, we get p is of the order of gm rho by r. So this means g m square by r to the power 4. Now, what about the degenerate electron gas equation of state? We have just used. So, degenerate electron gas, again non-relativistic, EOS equation of state. or basically pressure. So it will give me of the order of B. This B is basically contains all the other constants apart from your density. Okay, so this is of the order of B m to the power 5 by 3 and divided by r to the power 5. So basically we have used this relation over here to get this. Now if I use this equation and this equation together, that means if I equate the pressure together, then you will see what I get is this relation, R of the order of B by G m to the power minus 1 by 3. So what does this mean? This means that the radius of the white dwarf, R of white dwarf, basically decreases with increasing mass, right? Let's do an order of estimate calculation. So again, radius of white dwarf is of the order of B by G m to the power minus 1 by 3, and if I put in the various values, what I get is this: h square divided by 20 me mp to the power 5 by 3 into G and minus 1 by 3. So let's plug in all the values, and you see after plugging in, and we get the value as R white dwarf of the order of 1.2 into 10 to the power 9 centimeter, Z by A 5 by 3 into m by m solar minus 1 by 3. Now this is using a very basic approach that we have just done, whereas you see a full solution of the equation of stellar structure for degenerate gas will give us a value. The proper value will be again the same, but notice this: R white dwarf basically not, now let me write equal to 2.3 into 10 to the power 9 centimeter. Again all the terms are the same, only this is different, this constant. This is what I always tell you also. Remember to get these powers correct in your estimates. We can of course say a sort of approximation regarding the constant, but the powers in your calculation, they must match. They should be correct. Okay, now so if I calculate, so this calculates to be about 8,500 kilometer for Z by A is equal to 0.5 and M is equal to 0.6 solar masses, right? So this is what we get, and this is just as deduced for observed white dwarfs from their luminosities and temperature. Okay, good. So what are we going to do next? Next, what are we going to do is that let us talk about, till now we have talked about non-relativistic white dwarf. But as the mass increases, the electrons will become degenerate. So we will try to find that case. We will try to explore the case. And basically what we will be doing is that by equating the core pressure in a star to the degenerate pressure of ultra-relativistic electrons, we can derive an expression for the mass of a star supported by the ultra-relativistic electrons. Right? So, we would like to explore the mass of a white dwarf, where you see where the electrons are ultra relativistic, or basically you can say the mass of a star is supported by the pressure due to the gravitational pressure will be supported by the ultra relativistic electron pressure. Now you see the mass for this star, when the ultra relativistic limit is reached, it should be viewed as the maximum. So when ultra relativistic limit is reached, right, then we have maximum white dwarf mass, and this limiting mass, maximum mass, is known as Chandrasekhar mass, and its realistic values is around 1.4 solar masses. Okay, now what happens if the mass is further increased? So if mass is further increased, let's see what happens. So if the mass is further increased, the pressure needed to support the star also increases, but the ultra relativistic degenerate electrons will not be able to increase their pressure to support it. So we need something to support that pressure, and that something is basically the material supporting the star. And what will it be? Well, what comes to your mind? So apart from electrons, we have atoms, or basically protons and neutrons, right? Now you see there is a stable configuration of material at higher masses, but it is not degenerate electrons. Rather, you see the electrons and protons of higher mass objects are basically forced to combine as neutrons, and the stable object above the maximum white dwarf mass is called, so stable object above the maximum white dwarf mass is basically the neutron star. Fine. Now we will not talk about it in this class, but I have just laid down the basic background for it. So with these ideas, let us now try to estimate this Chandrasekhar mass. Now you see, so as I have been repeatedly telling you, the larger the white dwarf mass that we consider, the smaller. So larger the mass, this means the smaller the white dwarf radius becomes, implying that larger densities are possible, and therefore larger momenta to which electrons are pushed. So this means larger density or larger P for electrons to be pushed. Now when the electron velocities become comparable, so large momenta, right? So basically V increases. So what's the maximum V? V max, it is equal to your speed of light, right? So when the electron velocities become comparable to the speed of light, then we will have to talk about your relativistic, then ultra relativistic equation of state we will have to talk about, right? So let me write it down. The ultra relativistic equation of state compared to your non-relativistic equation of state, this one is little bit different. Let me show you. So 4 mp to the power 5 by 3 z by a whole to the power 4 by 3 into rho to the power 4 by 3. So what's the first thing that you notice? So differences. So this is for your ultra relativistic case. Okay, now differences with non-relativistic equation of state. Yes, so this one. What is the difference, do you notice? Now, the first difference is the 4 by 3 power. So, 4 by 3 power in density and z by a. Whereas, this is for ultra relativistic case, and this power is 5 by 3 for non-relativistic case. So this is the first difference. There is another difference as well. You see here in this case, in ultra relativistic case, mass of electron is absent, which was present in the case of non-relativistic case. So it does not appear in this equation of state. That means this equation holds for any ultra relativistic degenerate electron gas. So EOS ultra relativistic, it holds for any ultra relativistic degenerate gas of spin half particles, right? Now, why does this happen? This is because for ultra-relativistic particles, the rest mass is a negligible fraction of the total energy. And this is because, you see, rest mass, that is mc square, is much less than E. And so, we have P is of the order of E by C. And this is the reason why we do not have any mass of electron in this expression. Now, as we go from small to large white dwarf masses, there will be a gradual transition. So, from small white dwarf, say helium white dwarf, to large white dwarf masses, say carbon white dwarf, there will be a gradual transition. So, a gradual transition from your non-relativistic case to your ultra-relativistic equation of state will be there, right? And so this means the density dependence will gradually change from 5 by 3 to your 4 by 3. Now, what does this mean is that as we go to higher masses, so this means that as we go to higher masses and the density increases due to the shrinking radius, the pressure support will rise more and more slowly. So, P will rise more and more slowly so that radius shrinks even more sharply with increasing radius. So, this means radius shrinks even more sharply with increasing mass. Now, let us see what happens as a result. So, let us again rederive the scaling relations. Let us rederive the scaling relations again between mass and radius, but this time with an index 4 plus epsilon by 3. You remember, in the non-relativistic case, we have what is the value of the power? The power is 5 by 3. That is 4 plus 1 by 3. Sorry, this should be not 5. This should be 3. And for the ultra-relativistic case, the power is just 4 plus 0 by 3. So, this 1 changes to 0. That's why I have used this epsilon right here to see what happens as epsilon changes from. So, let's see what happens as epsilon approaches 0. Anyway, let us now write the pressure expression. So, pressure is basically, whether it is non-relativistic, whether it is relativistic, the pressure is basically 4 plus epsilon by 3. So, this means that m by 4 plus epsilon by 3 divided by r by 4 plus epsilon is proportional to m square by r to the power 4. You remember? So, this we get from your hydrostatic equilibrium scaling, and this we get from your continuity equation of scaling, that is rho is of the order of m by r cube. This we get, and this is just from the hydrostatic equation scaling. Okay, so what after? So this means that we can write, you see, r to the power epsilon is of the order of m to the power epsilon minus 2 by 3, and so this means r is of the order of m to the power epsilon minus 2 by 3 epsilon. So when epsilon tends to 0, what happens is that r tends to m to the power minus infinity. Understand? That means equal to 0. So what this means is that at a mass high enough so that the electrons become ultra-relativistic, the electron pressure becomes incapable of supporting the star against gravity, and the radius shrinks to 0. That means density rises to infinity unless some other source of pressure sets in. Okay. Now we will later see that at such high densities, the degeneracy pressure due to protons and neutrons begin to operate, and it can sometimes stop the full gravitational collapse, producing your neutron stars. Now, so this argument basically implies that there is a maximum stellar mass. So maximum stellar mass is there that can be supported by the degenerate electron pressure. And this is your Chandrasekhar mass. Now to estimate the Chandrasekhar mass, we will use the virial theorem. So, you remember from the virial theorem, we have this relation P average V is equal to minus 1 by 3 into E gravitation. Now, if I substitute here in this P average the ultra relativistic electron pressure, right? Ultra relativistic electron pressure over here, then you see, and your normal value for the E gravitation over here, which is just gm square by r. Okay. Then what we have is this. After you do this putting over here, I would like you to check for yourself that, okay, let me show this for you. So let me again write this 3 by 8 pi to the power 1 by 3 into hc whole to the power 4 mp to the power 4 by 3, again z by a to the power 4 by 3 v. This is of the order of 1 by 3 1 by 3 g m square by r. Okay, now we will use some more scaling relations as well. So with rho is of the order of mass by volume and V is equal to 4 by 3 pi r cube, what happens is that r cancels out in both sides and you can check that we will get something like this, m of the order of 0.11 into z by a whole square into hc by gmp square to the power 3 by 2 into mp. Okay, now as previously we have done, what I am going to tell you is that a full solution, again a full solution of the stellar structure equations will give me a somewhat larger numerical coefficient, and so the final result is like this: 0.21 z by a into hc by gmp square to the power 3 by 2 into mass of proton. Now you must be wondering why I have written this mp, mass of proton, like this over here and again written it like this. You see, this expression gmp square divided by your hc, what is this? You know, this term which appears in the Chandrasekhar mass is basically a dimensionless constant which can be formed by taking the proton's gravitational self-energy and the proton radius expressed by its de Broglie wavelength, and thus we get the ratio of the, and forming the ratio with the proton's rest energy. So let me show you how is this. So what I am saying is that let us name this as alpha g, and this is basically, so the ratio of protons gravitational self energy divided by your proton radius expressed by the de Broglie wavelength. Okay, and forming the ratio with the proton's rest energy, and so this is what we get. So again, what we have here is the proton's rest energy gmp square by r, and that r is basically expressed in terms of the de Broglie wavelength h by mp into c, and divided by the rest mass of the proton. So this is gravitational self energy of the proton divided by the rest mass of the proton. Understand? And this is the value. And if you do the calculations, then you will see that the value of this alpha j, it comes out to be approximately 10 to the power minus 39. Okay. Now you see this constant alpha j basically expresses the strength of the gravitational interaction and is the gravitational analog to the fine structure constant, which is E square by hc, see, whose value is of the order of 1 by 137. So you compare the two values and you get the idea of how much weak the gravitational force is. But given a very large mass, gravitational field can be dominating even above your electromagnetic interaction, and this is what we are seeing right now. Okay, now let us estimate this Chandrasekhar mass. So this is our expression for the Chandrasekhar mass. Now so assuming z by a is of the order of 0.5, okay. Right. So now before I do the calculation, let me again tell you what this expression means. This expression, Chandrasekhar mass expression, so you get this, there is a 0.21 into z by a whole square, right? So these two terms are there into another two terms, which is your alpha g, basically, which is alpha g to the power minus 3 by 2 into your mass of proton. So these two terms are there separately. What does this mean? This means basically that the maximum mass of a star, so this is the maximum mass, right? Maximum mass of a star supported by the electron degeneracy pressure is to an order of magnitude. Basically, what is this? This Chandrasekhar mass, if I take this as a constant of value of 1, this means that your Chandrasekhar mass is of the order of this alpha g to the power minus 3 by 2 into mp. So this means that your maximum mass supported by electron degeneracy pressure is to an order of the magnitude the mass of this much amount of protons, so many protons. And how many protons are there? If you calculate the value, then you will see that the number comes out to be approximately 10 to the power 57 protons. Okay, so now let me do the estimate. So let us assume that z by a is of the order of 0.5 and we have got this number as well. Then you will see that the Chandrasekhar mass comes out to be, assuming density of yes, this is the value. You don't have to assume density, just put in the values of this alpha g z by a and mass of proton, then you will see that it comes out to be around 1.4 solar masses. Now in fact it is very interesting to note that no white dwarfs with masses higher than this Chandrasekhar mass has been found. Fine.